Today we'll be continuing with the polynomial hierarchy, and so just to recall, the things that we did in the previous lecture. Remember that we were talking about problems, and maybe I should pull this out as well. We were talking about problems like exact clique and smallest formula, where essentially the definitions, at least the languages, involve some kind of alternation of quantification. And the polynomial hierarchy captures languages that are expressed through alternations of quantifications, with a Boolean formula at the end. So let me give you. There are actually many definitions of the polynomial hierarchy. So let me give you two, or sort of actually three, of the primary ones. So the first definition is through oracle machines. So it's a recursive definition. We discussed oracle Turing machines that basically can make queries to a language sort of for free or in unit time. So you define sigma 1 and pi 1, these complexity classes, to be NP and co-NP. That's how we start. And then we say sigma I plus 1, the class sigma I plus 1, is NP sort of to the power sigma IP. So what this means is an NP machine, a non-deterministic time polynomial machine, that can make queries to any language in sigma I. Okay, so for example, the sort of important class of sigma 2 is also written as NP to the NP, and pi 2 is co NP to the NP. Okay, so that is sigma 2 and that is pi 2. And then you have sigma 3, pi 3, so on and so forth, where now you would say, okay, consider an oracle to an NP to the NP machine, to the NP to the NP language. And what is an NP machine with that oracle access? What can that do? And that gives you sigma 3, so on and so forth. So that is one definition. The second definition is the alternating certificate viewpoint. So here what we say is L is in sigma I if there exists a polynomial time machine M and some polynomial Q, and Q is like some kind of bound on the certificate size. X is in L if and only if there exists U1 such that for all U2 there exists a U3, so on and so forth, alternating quantification such that M of X, U1, U2 up to Ui accepts. So if you set I is equal to 1, then you exactly recover NP. Sorry, piece of paper fell down. Okay. Right, so if I is equal to 1, then you don't have any of this, and this is exactly NP. And pi I is just co of sigma I. The polynomial hierarchy is the union of all the sigma i's, which is essentially the union of all pi i's. Okay, and what you can argue, and this is a small exercise that you can do, and you can see this just by the way the quantifications are structured, is that obviously sigma I is a subset of sigma I plus 1. It's not hard to show that pi I is also a subset of sigma I plus 1. So both sigma I and pi I are subsets of sigma I plus 1. And so just as a picture, what you get is this picture here. P is contained in NP intersection NP and co-NP, and both NP and co-NP are contained in sigma 2. Both of these are contained in pi 2. Sigma 2 and pi 2 are contained in sigma 3, so on and so forth. And you do this, and this gives you the polynomial hierarchy. The polynomial hierarchy is contained in P space, and we'll see why that is the case shortly. I mean, you can directly prove that, but we'll see that essentially special cases of quantified Boolean formula are complete for all classes in the polynomial hierarchy. So those were two definitions. Now the third, I guess it's not really a definition, but I like to think of it as a definition of the polynomial hierarchy. So let's define sigma I sat to be formulas phi, where you think of the formula has basically I inputs. Now each of those inputs may be many bits. So you break up the n inputs into I chunks, right? So this is not an individual bit. This is itself some kind of chunk of inputs. So phi is in pi I sat if there exists a u1 such that for all u2 there exists a u3, so on and so forth, switching quantification I times such that phi of u1 up to ui is true. Again, if I is equal to 1, this is just sat, the normal version of satisfiability. This is a special case of quantified Boolean formula. If I basically had arbitrarily many quantification switches, arbitrarily many quantifiers, then that gives me quantified Boolean formula, QBF. In sigma I sat, I am only allowed to switch the quantification I times. You can switch it at most I times. That's what sigma I sat is. Okay, any questions about that? So why did I say that this is a definition of the polynomial hierarchy? Well, one way to actually look at the polynomial hierarchy is really sigma I, the class, is exactly the class of problems that are all reducible to sigma I sat. So I could even turn this around and say that this is like a definition. But let's state it as, we'll state it as a theorem. Pi I sat, which is essentially the same as sigma I sat, except you start with a for all quantification, not whether there exists, is pi I complete. So this is like a really nice way in which you get a gradation between NP and P space, where NP is just sigma 1. And the polynomial hierarchy is, where you have sigma I sat, you have at most I quantification switches. So the polynomial hierarchy is a constant number of quantification switches, and P space is just arbitrary quantification switches. The agenda for today will be twofold. First, we will prove this theorem. Secondly, we will prove that the two definitions of the polynomial hierarchy that I gave are equivalent. Any questions? Any questions? All right. Then let us go ahead and proceed. And so we started off the proof of the theorem in the previous lecture. So let us use definition 2 for sigma I. So definition 2 was with respect to this alternating certificate definition. Okay? And now I'm going to prove that sigma I sat is sigma I complete. We proved by induction on I. The base case, pi is equal to 1. This is easy. This is the Cook-Levin theorem. That just says that sat is NP complete and tautology is co-NP complete. Because pi 1 sat is tautology, sigma 1 sat is the vanilla version of sat. Now for induction, let's assume for I. So we assume that sigma I sat and pi I sat are sigma I and pi I complete respectively. Consider a language in sigma I plus 1. We need to prove that this language can be reduced to sigma I plus 1 sat. Okay? Now using the definition, I guess technically, of sigma I plus 1, we know that there exists a Turing machine M that runs in polynomial time, and there exists a polynomial Q such that X is in L if and only if there is this sort of alternating certificate. There exists a U1 such that for all U2, so on and so forth, up to UI plus 1, such that MX U1 U2 up to UI plus 1, those are all the inputs to the machine M this machine accepts, right? And UI has at most polynomial size. Now the argument that you are going to see here is very common for understanding the polynomial hierarchy. I will create a new language L prime, where L prime is defined with respect to only I alternations. How do I do that? I take the first part of the certificate and simply fold that into the language. So I say, well, I could look at the language of x comma u, where x is in L and u1 is the first certificate. So I look at pairs x comma u1 such that for all u2 there exists a u3, so on and so forth. So at mx u1 u2 accepts, right? So I just took this existential and kind of shifted it and made it part of the language. So I get a new language, but there are only I alternations here. This language L prime is in pi I. Now I can use induction. I can say L prime is reducible to pi I sat. Okay, now let's dig a little deeper into what that means. That means there exists a polynomial time, I'll call it the reducer. This is the reduction given by induction, that given pi and x u1, right, which is in the language as input, computes a formula phi x u1 which takes I inputs. Remember, this is sort of the analog here. It takes I inputs such that x u1 is in L prime if and only if this formula is in pi 1 sat. Right? This is just opening up what it means for the reduction. Any questions at this point? Any questions? All right, if there are no questions, then let me go one step further. I'll say, well, okay, so x is in the language if and only if there exists a u1 such that x u1 is in L prime. Right? This is the way we set up L prime. And this is if and only if phi of x u1 is in pi I sat. So x is in L if and only if there exists a u such that phi x u1 is in pi I sat. Right? And all of these are of polynomial size, like u1 is of polynomial size, so on and so forth. Okay. So let's just write that down. We say x is in L if and only if there exists a u, which was the u1, such that for all v1 there exists a u2 up to vi, such that phi x u, right? This is some formula of v1, v2 up to vi is true. There is a quantification over the formula. The formula is not fixed. The formula is itself like a variable because the formula depends on you. Now, what we really want, let's go back, let's step back and say, what is it that we wanted to prove? We wanted to prove that L can be reduced to pi I sat, sigma I plus 1 sat. So given x in polynomial time, we wish to compute a psi, which is some formula of z1, z2 up to zi plus 1. So I'm just using another set of variables, such that x is in L if and only if psi of z1 up to zi plus 1 is in pi I sat. Which is the same as saying that there exists a z1, so that for all z2 there exists a z3, so on and so forth, up to I plus 1, such that psi is true. Now, psi is some function of x. Now, it looks like we're getting there because the number of quantification switches that we had here was I plus 1. The annoyance is that this formula shouldn't depend on u. It should only depend on x. Whereas here, it actually depends on the u and there's an existential over the u. So we don't even know how to compute this formula just as a function of x. So we're going to have to be a little clever to construct a formula over here. Any questions at this point? This is a subtle point. Like I really want to sort of make sure that you understand this point. I'll pause here, let you read this, and let you digest what's going on. Please ask me questions if this doesn't make sense. Questions? This is clear.
I'm still feeling a bit confused about the relationship here between phi and phi and psi.
So
can you repeat?
So C is something that we want to compute. We're still trying to figure out how. Okay, so suppose you could do this. Ignore all of this. Suppose we could do this. All right. Suppose given L, we could compute in poly time. We could compute C, such that this is true. All right. If we could do this, then we have reduced L to sigma I sat.
Sure.
So this is what we would like to achieve. What we have achieved through induction is what's given here.
Okay. Oh, sure. Oh.
Now I want to go from here to here.
Okay.
Does that help? Does that make sense now?
Yeah. I see what you're getting at now.
So, and it seems like I'm almost there because I got the right number of quantification switches. Which is not surprising because I started with L being in sigma I. The problem is that I don't really have a formula there that's a function of x. It's a formula which is a function of x and u. So it's almost like saying that there exists a u such that some function of x and u will create the right formula for me. Whereas here, I want to compute an explicit formula given x. So we actually going to have to invoke like the Cook-Levin theorem to get there, or rather the techniques within the Cook-Levin theorem. So let me sort of take this and let me just rewrite that. I'm just going to say x is an L if and only if there exists a u such that for all v1 there exists a v2 up to vi such that, I'm going to write this out sort of in gory detail, such that denoting by phi of xu, denoting by that the output of the reducer denoting by this, so I'm saying that phi xu is really the output of the reducer that we had defined earlier. And again, that reducer was what we got through induction. The reducer gave us this phi of xu, right? So there is this polynomial time reducer that gives this formula. So denoting by that the formula. I'm going to write some stuff down and then I'll explain what I mean. F of xu1 v1 v2 up to vi outputs 1. So what is f? Let f be a, and this is a polynomial time Turing machine that takes as input a formula. So it's taking as input the formula phi, and I'm just going to use z to denote its argument. So it's going to take as input a formula c and evaluates so it's almost like I'm doing something, I'm just writing this out in somewhat gory detail. I'm just saying that f is a Turing machine that simply evaluates the formula. So let's go back. We're saying x is an L if there exists a u1 such that for all v1 there exists a v2, so on and so forth, such that if you run R on x and u1, you're going to get a formula phi of xu. And if you evaluate phi of xu on v1 up to vi, that outputs 1. But what does it mean to evaluate that? We'll say, well, there's some polynomial time procedure that actually does that evaluation. So the way I want to think of this is really, I'm going to draw a picture. X is an L if and only if right? So there exists a U, so that's being fed. And here is R. So R is going to be, so X is being fed. If there exists a U to feed, so this is going to output a phi. This is what we call phi XU. And now I'm going to feed this to F. And what does F say? F says, okay, so for all V1, there exists a V2 up to Vi, right? Whatever the quantification is. So this outputs 1. So does this make sense? X is an L if and only if this is true. Okay? Now, for convenience, I'm going to combine all of this. I'm going to combine all of this into one machine. This is just some machine. Because you feed the machine X, U, V1, V2, so on and so forth, right? You give it all of these inputs, and it is going to then spit out 1 or 0. Right? It's going to either spit out 1 or it's going to spit out 0. It's just some machine. Let me refer to this machine, this combined machine. I'm just going to call this as N. I don't want to call it M because I've used M before in the proof. This machine is N. So this is a machine that's going to take I plus 2 inputs. It's taking the I inputs that are the VIs, it's taking U as an input, and it's taking X as an input. So all of these inputs are coming in. There is all this quantification on these inputs. But the machine doesn't care about the quantification. The machine is just taking a bunch of inputs, and it's going to run R initially on X and U. It's going to get a formula. Then it's going to feed that formula to V1, V2. So this is just some procedure N. Right? This is just some procedure. Okay, so any questions about this? So this is, in some sense, back to the original definition, right? I have all these quantification switches. My problem is, I want to sort of convert this. Okay, so let me try to see if I can, what's the best way of saying this? Okay, so I don't know. So I think I may have, in some sense, overcomplicated the proof, but let me just go ahead and say what I'm going to say. So we have X is an L if and only if, you know, all of this is true. So let's ignore the N for now. Sorry. So this is sort of the overall picture. And what I'm going to say is, let me write this in the following way, such that if and only if there exists a U, there exists a phi. This is, again, you can non-deterministically guess what the phi is, such that for all V1 there exists V2, so on and so forth to Vi. Right, there exists this such that R of xu outputs phi, and and f of phi v1 v2 up to vi outputs 1. The reason to do this, in this what gets complicated is what is being fed into here is actually the output of something. And so it's a little hard to sort of write that out explicitly. But here what we can say is that once you fix u phi v1 v2, there's no quantification left in here. So all of this is now just well defined. There is no quantification left in here. Okay? And so we just need to replace by a formula. We just need to replace this statement by a formula. Does this make sense? And this is exactly what the Cook-Levin theorem does. Cook-Levin construction says something like, it says that M accepts X if and only there exists a tableau, satisfying logical conditions. Now this is actually a deterministic procedure. So the fact is the tableau is actually, there's only going to be one accepting tableau. And this tableau is actually unique for the case of a deterministic Turing machine. So M accepts X if and only if there exists a tableau satisfying some logical conditions. And if you recall, we were able to convert this and say if and only if some C is satisfiable, where C is a function of X. So what one does is that what is in this box is simply some deterministic procedure. It's just some deterministic procedure. So what we write is, for simplicity, let me just assume that I was even, and so the last one was that there exists. This is just going to be for convenience, and you can actually get rid of this assumption. So we'll just say that X is an L if and only if there exists a U and a phi. So again, this is just one quantification, such that for all V1 there exists a V2 all the way going up to there exists a Vi, such that there exists a tableau represented by the Boolean, represented by a string of Booleans Z, if and only if there exists a tableau represented by a string of Booleans Z, such that phi psi is satisfiable. And the inputs to psi are all of these things. And this now becomes, because you can combine these into just one quantification, there's no quantification switch, and you combine these so there's no quantification switch over here as well. This basically gives a sigma I plus 1 sat instance. It's a bit much to, it's a bit to take in. Right, so the thing is, once you get it down to this stage where there's basically some computation that's being done, you can always represent computation by a formula. And that's what Cook-Levin says. Right? Cook-Levin converts the existence of a tableau to some kind of to a CNF. And there's just some sort of mechanical procedure that does that. So you replace this by a formula, and that's it. Does that sort of make sense? Any questions?
I have a question.
Yeah.
So for our box, when we have f of that function, do we need to have, for example, for v1, that says like for all v1, like doesn't it not matter what v1 we choose? Like why do we need to include that in the function?
Why you need to include that in this function?
Yeah.
No, so think of it as, so let's sort of go back all the way down to what we initially had. We said that X is an L if and only if there exists, whatever there exists for all, such that this formula evaluated on V1 to Vi is true.
Right.
So you're just saying that I can encode. So here it's like there is a formula which is itself a variable, which is being evaluated on a bunch of variables.
Right.
But I encode all of that just by some formula. Like imagine if I can
really more about the encoding.
I'm sorry?
So it's really about the encoding.
Right, and so how did I encode this through a formula? Because this is a variable. Who knows what kind of function, but this is itself computed by a machine. Right, so this is computed by the reducer.
Right.
And so you can represent the running of a reducer again through a formula.
Okay.
Maybe the way to think about this is whenever you have a polynomial time machine, you can basically represent all of its running by a polynomial time formula.
Okay.
Like the entire, so think of the transcript, which is essentially the transcript is like the configuration strings one after the other. Each individual sort of, bit in the tape, all of that can just be represented by a formula. It's like, does there exist a way of setting all of these Boolean variables so that these conditions hold?
Gotcha.
Right? So I can basically fold all of this, the construction of this, and evaluating it on a bunch of things just by some formula, because this is like some explicit Turing machine that I have.
I see. Okay, sure.
So I mean, I'm going to have to think about this a bit, because as I was talking about this, I realized maybe there's a much simpler way of doing this, and I need to sort of evaluate if that is correct. And I'll just tell you, and then I have to think about it. It seems like just by the initial definition itself, I wonder if it's just more direct. I mean, the original definition says X is an L if and only if there's some alternation such that M accepts. But I think that you could just directly encode this machine accepting through a formula. In which case,
it seems like that's what we essentially just did, right?
Yeah, so we may not have had to even do all this induction to get there. So the only issue is maybe there's, one has to be a little careful in tracking the size of all of this, but I think the sizes and all will work out. So indeed, really the way to think about this is what Cook-Levin says is that the acceptance of a Turing machine can be encoded as a formula, which is the CNF.
I see.
Now the problem is, I kind of fudged the thing. I said that the last thing has to be there exists, otherwise it doesn't work, right? Because the way that I set it up, I kind of folded in these last two things together. We're saying that that was not a quantification switch. But what if this last one was a for all? Right? So then I can't do this. Now I'm going to say something. Essentially, what happens is, because this is a deterministic Turing machine, there's only one tableau that satisfies all the conditions. It's deterministic. So you can write this part equivalently as saying for all tableaus, if tableau is valid, like tableau is valid implies output is 1. Like I can basically replace the there exists with a for all, because it's a deterministic machine, because I know there's only one tableau that's going to satisfy things. Right? If it's a non-deterministic machine, some valid tableaus may lead to 0, some may lead to 1, and you have to consider all of them. But here it's just saying that if there is a valid tableau, the output is 1. So I can replace the there exists with also a for all, and therefore I can fold it with a for all. Right? So this is it's a bit technical. But that's the idea.
Could you also like potentially add like just a dummy variable like that's equisatisfiable to the original formula, and then just add another layer like for exists at the end?
If you add an extra layer, you will increase the number of quantification switches.
Right. But is it possible that even so, that like it would still be equisatisfiable?
You could. You could keep things that are equisatisfiable, but you want to make sure the number of quantification switches is maintained.
Okay.
Right? So the thing is, the number of switches is exactly I plus 1. So you don't want yet another switch to make it I plus 2, because then you would end up in sigma I plus 2 sat and not sigma I plus 1 sat.
Right.
Yeah. So, when you step back, I mean, it looks like a lot. It's basically, once you get the idea, it's sort of a tedious calculation. The idea is that the running of Turing machines by Cook-Levin can be encoded through formulas. The acceptance can be encoded through formulas basically by trying to guess the tableau and checking that the tableau is correct. Right, and that's the key. So where this leads us is that we now know that sigma I plus 1 sat is sigma I complete, pi I sat is pi I complete. The next thing we need to do is to prove our next theorem, which we're going to prove is that really definition 2 and definition 1 are equivalent. So let's recall what these are. So that's just saying that sigma I p defined as sort of all let me just sort of write it out so that I have exactly what I wrote out earlier. Yeah. Such that, L is in sigma I p if there exists a poly time Turing machine M and a polynomial Q such that X is an L if and only if there exists a U1 so that for all U2 up to UI where M x1 mx u1 u2 dui accepts, right? This was the first definition. This was actually definition 2. And definition 1 is simply is that sigma I p is np to the sigma I minus 1. So we want to show that these two are the same. And so we'll see that one side is actually pretty easy and the other side is more complicated. So let's prove one side. We'll just, the first part we'll prove is we'll say that if L satisfies definition 2, then L is in NP to the sigma I minus 1. Okay. So, sort of again, the way to think about it is that, let's go back to this definition, and we say that we define L prime be the language x u1, right? So we take this and we shift it there, such that for all u2 there exists u3 up to ui, such that m x1 u1 u2 to ui. We could even put this together, accepts. And so the whole point is that L prime is essentially in pi I minus 1. There are I minus 1 quantification switches. Or another way to put it is that the complement of this is in sigma I minus 1. Right, so now let me show you why L is an NP to the sigma I minus 1. Because if you want to define an NP machine for L, the NP machine would guess UI and just query whether this is in the language or not. Remember that when you have an oracle, having an oracle to the complement language and to the language are the same thing. So let me just write it out. Write out an NP machine. So here is an NP to the sigma I minus 1 p machine deciding L. Okay, so first, like, non-deterministically guess u1 of polynomial size, right? Whatever polynomial is appropriate over here, and query. So you can basically make a query of x u, and if you wanted to be really, sort of exact, you query, is this in L prime in the complement, and this is where the oracle call to sigma I minus 1, to a language in sigma I minus 1, and it'll just switch the answer. So this is almost like syntactic, the proof, right? Because the fact is, if you look at what this definition is, using NP machine, you can non-deterministically guess the first part, and then you just have to make a query to a pi language. But making a query to a pi language is the same as making a query to a sigma I language. All right, is that clear? Questions? Okay. So that was the easy part. Now for the hard part. So part 2, let's say part 2 is to say, suppose L is in NP to the sigma I minus 1p. We need to prove that L satisfies definition 2. Here is the problem. If you go back to what definition 2 does, it's kind of like saying that there exists a U1 so that one condition holds. This is like one query to a sigma I minus 1 or a pi I minus 1 language. So this is one query to a pi I minus 1 language. Whereas a machine of this form can make many queries to a sigma I minus 1 language. Does this make sense? Do you see the difficulty in just reversing this proof? Like, imagine an NP machine that would first make a query, get an answer, then do something, then make another query, then do an answer, then get another query. So it could make all of these queries, does all of this stuff non-deterministically, and makes all these queries. But in definition 2, you're only allowed to make a single query. Right? Because you can think of it as this is like a single query. Once you choose there exists a U1, then you have to do this. Does that make sense? Do you see the challenges there? Okay, so let me just draw out a picture, and I think, once I draw out the right pictures, you'll see what's going on a lot more easily. So let's consider L, and let's say consider NP to the sigma I minus 1p machine deciding L. Okay, so there's some machine. And over here, we're going to have this is the oracle. Now, if you think about it, because sigma I minus 1 is complete, you just have an oracle to sigma I minus 1 sat. That's all you really need. So what does this machine do? It's going to take as input x. Now it's going to do some non-determinism, which I represent by y. This is the non-determinism. The non-determinism. And then it's going to query for sigma 1. It's going to get some response. Then phi 1. It's going to query for phi 1, get a response. Query for phi 3, get a response, so on and so forth. Right? That's basically what this machine does. Okay? So it's natural, again, like, when we do this sort of non-determinism, we could always shift it to a certificate viewpoint. We could always shift it to a certificate viewpoint. And so let's construct the same thing. We can say here is x, here is y, which is like the NP certificate, right? Because the NP part has some certificate. And then the benefit is now this M becomes, let's call this M prime, becomes deterministic. This is deterministic, right? And then what it does is it does phi 1, it gets a response, it queries for phi 2, gets a response, so on and so forth. And this is the oracle to sigma I minus 1 sat. What we want is really a machine n that does the following. It should take x, it should take y, and it makes one query. I'll call it C. It gets a response. That's all. So instead of many queries, it should only make one query. Because if it makes one query, right, if it makes one query, then we could write this as definition 2. We could write this as definition 2. Because if it makes this one query, then essentially that okay, so let me first go from here and show that why is it that if we have this situation, we're done. Okay? Why is it that if we have this situation, we are done? So if we could prove that, then we would say that x is an L if and only if there exists a y such that n accepts. There exists a y such that n accepts. Now, okay, so let me write this as if there n accepts. And note that C is just some polynomial time computable function of x and y, right? C is some function of x and y. And so the response to this is, either 0 or 1 or whatever. And so the way to think about this, so thinking about the best way to say this, okay, so x is an L if and only if there exists a y such that n accepts where C of xy is the only query that is made. So this is the same as saying there exists a y such that, so let's see, remember C of xy is something that is in v1, v2 up to vi. So the point is, this, it may be in pi I sat, it may be in sigma I sat, it might not. So I'm sorry, let me So let me actually show you. Okay, so let me sort of step back for a second and say that intuitively this is what we want to do. And I'll actually explain, I think once I do the proof, we'll see why this leads us to the answer. But the first step is going to be that we start with a machine that's making multiple queries. That's making multiple queries to a sigma ISAT oracle. And I want to convert it just to have one query. Just have one query to a sigma ISAT oracle. Okay? So the key is, let's go and look at this. Phi1 is some polytime function of x and y. Phi2 is a polytime function of x, y, and b1, where b1 is the indicator for Phi1 being in sigma I minus 1 sat. And now Phi3 is a polytime function of x, y, b1, and b2, where b2 is the indicator of Phi2 being in sigma I sat, so on and so forth. Right? So these are all the queries made to the sigma ISAT oracle. What I'm going to do is I'm going to fold all of these into the non-deterministic, into the certificate. So I'll write this as follows. I'll say that because what's important to note is that the constructions of the phis are all done by this machine. It takes in the answers and it constructs the machine. It constructs the formula. The oracle is only deciding whether a formula is in sigma I minus sigma I sat or not. I guess technically this is sigma I minus 1. All of these are just polynomial functions. So we could non-deterministically guess what all of these are in one go, and then just check if those are the answers. So let me write this out carefully. I'll say that x is an L if and only if there exists a y, there exists a Phi1, there exists a b1, there exists a Phi2, there exists a b2, so on and so forth. For how many ever this makes some polynomial number. So this makes, let's say at most p of n, right? It makes phi of p of n. So it makes p of n different calls. There are p of n of these. So up to sigma p of n, sigma b of p of n. Where again n is the size of x, such that for all I going from 1 to p of n, phi of I is exactly the ith formula generated, and b of I is the right indicator, right? So the b of I is the right indicator for phi of I being in sigma I minus 1 sat. Okay, so far so good. So it's a bit clunky to write all of this down, but essentially what this means is this condition can sort of be checked in parallel for all the i's. So you basically list out a bunch of different formulas. That's phi1 up to phi pn. And you list out a guess for, do you think this is in the input or not? Do you think this is in sigma I sat or not? And that's that. And so if you guess all of these correctly, that means all of this interaction has been guessed, which means that one can run the machine M prime. And I claim that all of these guesses can be in some sense verified through a single sigma I sat, kind of like a single sigma I sat query. And the way one would do this is, let me write it in the following way. So I'll just say that I want to write sigma I basically, so actually I is probably not the right, because we're using I for, so each sigma j here is going to have, as its input, it's going to have uj1, uj2 up to uj I minus 1. I'm just writing this out. And we want to check if b of j is 1, then this should be in sigma I minus 1 sat. And if b of j is 0, then sigma j of all of this should not be in sigma I minus 1 sat. So all of these are sort of the checks that need to be made. And this needs to be done for all the j's. So the way that I'm going to do this is I'm going to say x is an L if and only if there exists a y, there exists a phi1, there exists a b1, b of pn, such that now I can go ahead and I can start making my queries in here. So it's a bit okay, so it's a little bit clunky, but let's just assume so you say there exists all of these, right? And sorry, I'm not expressing myself very well over here. So I'll say there exists. Let me just write something down over here, and we'll see. uj1 sorry. If bj is equal to 1, then I want to do there exists uj1 for all uj2 up to uj I minus 1, and if b of j is 0. If I had chosen 0 over here, then the quantification that I'm looking for is to say for all uj1 there exists uj2, so on and so forth. So this is going to then be false. Right? So I have sort of this condition for all j. And these are all independent of each other. So I can essentially interleave them so that I don't have to keep switching quantifiers for all of them. What I mean is I can write something like there exists u11, u21, u31, u41 up to u pn of 1, such that for all u12, u22, u32, u42 up to u pn of 2, such that there exists u13, u23, so on and so forth. So there exists for all of those, for all of these, there exists, so on and so forth. So this gives me my I quantification switches, and this is going to go up to ui minus ui I minus 1, u2 I minus 1, so on and so forth. So that's all the quantification I do. So let me just ignore this for a second. Once I do all this quantification, now what I need to check is if b of j is equal to 1, then phi of j with uj1, uj2, so on and so forth is true. And if b of j is 0, then I do phi of j uj1, uj2, so on and so forth is false, and phi of j is the ith formula computed by n, by m prime, this machine. Okay, so this is a bit much, but what's going on is all of these queries are being non-deterministically guessed and then sort of verified in one go. And you can verify them because once you fix all of these individual expressions, so you fix all of these expressions, each of these has some sort of quantification switch. But you can interleave all those quantification switches into each other. You can just interleave all of them. Does this sort of make sense? And this is now just something done by a deterministic Turing machine. Like this box is something that can be done by a deterministic Turing machine. So in some sense, the first thing you check is whether all the guesses are correct. And if all the guesses are correct, then you can just go ahead and run m prime. And this is kind of like making one query. It's not exactly making one query. So that's why this picture was a little misleading. But it's kind of like clubbing all of them together through this process where you basically interleave all of these so that you're only making, whatever, I minus, there will be a total of only I quantification switches here. Does this make sense? So please ask me questions. I know that this is, I was a little clunky with the notation. I was not happy with my notation. But, and that's why sort of I slowed down. My notes, I think the notation isn't perfect. And I may have to refine the notation a bit. but this is like the main idea. The main idea is there are all these queries being made to a sigma I minus 1 sat oracle. The NP machine can actually non-deterministically guess the queries and the answers. So it non-deterministically guesses all the queries and the answers up front, and then just goes and verifies are all of these guesses correct. And that can be done by a single level of all, like it can be just done by a bunch of alternations where once you've guessed the formulas, you then have to do a there exists for all the inputs to check all of these conditions. I fudged a small detail here which I will explain shortly, but then hopefully this makes sense. Questions?
Wait, so in the end, we're not doing only one query to the
Yeah, it's not really one sigma I sat query. It's actually running a Turing machine here. But then remember that because this is all like, sigma I sat is complete, you can convert this to making one query.
Wasn't the original problem that we were making that we were not making one query?
Yeah, original problem is so I guess what we really want is this definition.
Right.
And I'm now giving you this definition because this M that I have here is this block over here.
Right.
So you think of it as I started with this. I started with the machine that was making lots of Oracle queries. And what I'm going to construct is this. Okay, so should I go over the argument again? I mean, I can poll you and ask you.
Yeah, I think that would be good for me.
Yeah, I think. Let me sort of go over the argument again. Okay, so I think that would be useful. All right, so L is in NP to the sigma I minus 1. We wish to construct a polytime Turing machine N such that X is in L if and only if there exists a U1 such that for all U2 up to UI, N of X, U1, U2 up to UI accepts. So we just need to construct this one polynomial time machine that has this structure. So what we have here, okay, so now let M be the machine in, or be the NP to sigma I minus 1 machine accepting L. Okay, so what is going to happen is that we can write this as let M prime be the, so that there is a non-determinism that we can kind of fold out. So let's just say it's the P, the sigma I minus 1 machine P accepting L prime equal to, X is an L and U is like the first certificate. Right? And I'll call this Y. Right? So I'm just rewriting this. I'm just saying that what you end up with is a machine M prime, which is deterministic. That's why I call this a P to the power sigma I sat, which now takes in as input Y as well. Okay? What we want is actually a machine in P. We have this funny oracle machine. So how do you simulate M prime? How do you simulate M prime? So you guess the behavior of the oracle. Okay, so let's sort of stop here. And let's say how to simulate M prime. And that's what this machine N is going to do. N will simulate M prime. But N is a polynomial time machine. N is just a polynomial time machine. So N needs to know the formulas phi that M prime queries and needs to know the answers. So what we can say is N x, so let's just take M prime, right? And M prime is going to take as input xy. Let's say queries formulas phi 1, phi 2 up to phi of Pn and gets answers B1, B2 up to B of Pn. Now, if N knows what these are, then N can just simulate M prime. Because N would then effectively, so N would in effect simulate the oracle. If it knew all the answers and knew what was being constructed, it can just simulate this entire M and then see whether, see what the output is. Does that make sense? Questions? So this guessing can be folded into the initial non-determinism over here. But then we have to verify that the answers are actually correct. So we can think of N is going to have two parts. First is just going to check, are all the formulas, are the answers to the formulas correct? Are the answers to the formulas correct? And if the answers to the formulas are correct, then it can go ahead and do the simulation and just check that the formulas being generated are the correct ones. Okay? So here is how we're going to state this. We'll say that X is in the language if and only if there exists the initial certificate Y, there exists phi 1 going up to phi of Pn, there exists B1 going up to B of Pn. All of these are existentials. Now we're going to use the alternation to actually verify if these things are correct or not. And the way we're going to do that is now we're going to do I minus 1. We're going to do I minus 1 of these. So we'll say, so I'm going to do this a little carefully now so that and remember, we'll say that phi of j takes as input uj1, uj2 up to uj I minus 1. So I'm going to first guess there exists. I'm going to use other symbols here. I'm going to use y and I'll use w and z. W11, W21, W31 up to WPN1. I'm also going to take for all Z11, Z21 up to ZPN1. Then I'll do, you'll see what I'm doing and it'll start making sense. So I do everything for the first one, 1, 2, W22, W32 up to WPN of 2. And then there's going to be a for all of Z22, Z21, I'm sorry, Z12, Z22, Z32, ZPN of 2. Sorry. You'll see that I'm switching. There exists over here and a for all over here. I'm going to use these separately. Then W13, W23, WPN of 3, Z13, Z23, PN of 3. So this is going to keep going up to I minus 1. This is going to keep going up to I minus 1. And you'll see that the total number of quantification switches is going to be I. Because if I go up to here, I get 2 switches. If I go up to here, I get 3 switches. If I go up to here, I get 4 switches, right? Because this is all 1. Then there's 1 switch. It goes here. There's the next switch. And then there's a 3rd switch. Right? So these are all the switches that I get. Okay, why am I doing so? These are all the variables. This is all the quantification that I'm doing here. Okay, now once I have done all this quantification, what is it that I'm going to check? I want to check if B1 is correct. I want to check if B1 is correct. So what I'm going to do here is I'm going to say if B1 is 1, then phi j of bj is 1. So I'm going to do this for all j less than p of n. This is not a quantification. This is like a for loop in my procedure, right? So now this is all the quantification. Now here I'm going to define my procedure n. I'm going to say for all j, if bj is equal to 1, then phi j, I have to now verify that this is actually going to do the correct j1, wj2 up to up to wj I minus 1 is true. If b of j is 0, then I have to flip my quantifier. So I use the z's instead. Z j1, z j2, zj I minus 1 is false. Once I've checked these, then I check that, then I simulate m prime, check the phi j's are generated, and the final output is accept. right? And this gives me the machine n. Okay, so sorry, this is a bit, you're gonna have to go and look at this, but this is essentially how I convert the fact that there were multiple queries essentially into something that looks like only one query. I mean, it's not really one query, but it's combining all of these things into just one polynomial time Turing machine, and I can get all the quantification to go out in the beginning. Hopefully this makes sense. Any questions about this?
I think that clarifies things for me. Yeah, thank you.
Okay, so I want to step back and say there's sort of one, although this is only like, a few minutes left, there's one last thing that I want to say, which is really important with respect to the polynomial hierarchy. And even, if you didn't get the proof completely, that's okay, as long as you understand what the polynomial hierarchy is. There is a very important concept which is related to complexity theory, which is, I guess all of this is related to complexity theory, an important complexity assumption. Just like we have P is not equal to NP. P is not equal to P space. L is not equal to P. Here's another one, and this is called the collapse of the polynomial hierarchy. The collapse of the polynomial hierarchy is, so this is a claim that says if sigma IP is actually equal to pi I, then the polynomial hierarchy is just sigma I. And this is called collapse. What this says is, if any of these two become equal, then the polynomial hierarchy goes all the way down to that. What this says is, another way to say this is, at this point, if the polynomial hierarchy is just sigma I, it says that if you have more quantifications than I, if you have any constant number of quantification switches in sigma I sat, you can just convert that to I quantifications. Meaning that if you take sigma j sat, where j is larger than I, there is a polynomial time reduction to sigma I sat, if this happens. So this essentially I leave as an exercise. You can prove by induction. You can prove by induction over J that sigma J is going to be contained, that for J greater than I. You can prove this by induction, and indeed there's a version of this exercise that I've given in the homework, and this is called the collapse of the polynomial hierarchy. Most complexity theories do not believe that the polynomial hierarchy will collapse, just like we don't think that P is going to be equal to NP, and therefore we use that assumption. We use the fact that P is not equal to NP to prove hardness, which is what NP completeness is all about. Similarly, an assumption is that the polynomial hierarchy does not collapse. This is a stronger assumption than P is not equal to NP, because if P is equal to NP, the polynomial hierarchy collapses to P. If P is equal to NP, then all of the polynomial hierarchy just becomes P. If NP is equal to co-NP, the polynomial hierarchy collapses to NP. So the collapsing of the polynomial hierarchy, in some sense, generalizes and is a stronger assumption or a stronger conjecture than the conjectures of P not equal to NP and NP not equal to co-NP. What it basically says is that when you do more quantification switches in sigma I sat, the problem fundamentally becomes harder. And that this you cannot reduce by you can't have efficient reductions from more quantification switches to fewer. And that's basically the idea of the collapse of the polynomial hierarchy. Okay, so this is a good time to end. I'll end the lecture here and I'll take any questions that you have.